Okay, hello, my name is Elena Dolgas. As we said, UV vis analysis of silicic lunar red spots. I would like to thank Lunar Vice for funding this work. And next. So a little bit of history on why I'm interested in the UV vis. The UV vis lunar spectral reversal phenomenon. So the Apollo 17 UV instrument first noticed this spectral phenomenon in which areas that appear dark in the UV were bright in the visible, and the reverse was true. So at the time, this was linked to bulk composition, so there were opaque minerals causing this spectral difference. However, as we got more instruments and more observations of the moon, such as our LAMP or the Lyman Alpha Mapping Project, which is also a UV spectrometer, it was found that this is not only composition, but also hydration and weathering. And next. So lunar red spots, a brief history. Spectral anomalies, they were found with telescopic filter imaging, and they were found to be these regions that were strong UV absorbers, so they are red in the UV compared to the blue mare. These are usually associated with areas of non-mare volcanism. They're usually highly silicic. There's often high glass content, and they are also associated with PKT. And next. So from that large list of red spots, I focus on the silicic domes. So of interest to Lunar Vice in particular, the Griffith domes. So the Gamma Dome and the Delta Dome, these two areas are proposed to be highly silicic volcanic features. And then Hansine Alpha is an isolated silicic dome. It's a little bit flatter than the Griffith domes. It is comprised of 3 distinct geologic units, so it likely went through multiple stages of this evolution. And then last, the Compton-Belkovich feature, which is on the only far side lunar red spot. And what I have circled there, or what I have in the box there, is where thorium anomaly measurements were observed. However, it is a complex region, including several small domes. And next. So tying these two together, how do we link spectral reversal in the UV vis to red spots? So LAMP studies have continued to observe the spectral reversal, so that is confirmed. However, there is limited far UV analysis of red spots. There's also limited UV vis analysis of red spots. So in the visible, we have data in which lab studies were conducted that revealed that increased reflectance at these red spots could be accounted for by the increase of pumice or glass. And then in the IR, so moving wavelengths a bit, the differences in these red spots could be accounted for because of fine grains on their surface, and particularly at Compton-Belkovich, perhaps pyroclastic materials. So this all leads me to my, could you go back? This leads me to my science question: how and why does the magnitude of the UV vis spectral reversal vary among these lunar red spots? So the 3 in particular. And next. So the first, these will all follow the same format. These are LAMP albedo maps, which are based on counts received. So these are daytime maps, and the figures all have the red spot in pink and then a Mare region black. For the case of the Griffith domes, I have 2 regions of interest, the Gamma Dome and the Delta Dome. So as you can see from this albedo that we're going to call it plot, the domes appear darker than the Mare. So this is not surprising. Other studies have found this previously, but it's likely attributed to their highly silicic nature. It's possible that there's also some Mare pyroclastic mixing, though this has not been confirmed. Next. So zooming in at those features, so these are all normalized reflectance spectra, so they are divided by highlands just to remove that general slope effect that you see in spectra. And each box is then averaged across all wavelengths. So the Gamma Dome and the Delta Dome appear darker than the Mare. This is not surprising. And the spectral reversal was clear for the Mare region of interest. There is a flip that occurs between the 2 domes, but what this flip is from, we aren't sure yet, though it could be because the Gamma Dome has 2 large impact craters and perhaps has more mixing. Next. So the same type of LAMP map, the Hansine Alpha feature is in pink, Mare is in black, and we see again it is darker than the surrounding region. And then in terms of magnitude, it is a bit darker than the Griffith domes. It could be because this is less silicic, however, we still are verifying these results. And next. So looking at the spectra again, this region of interest, the Mare spectral reversal is very evident. There isn't much of a reversal for Hansen alpha. So this could be because of silica content or because of space weathering or a combination of other factors, but it is likely due to regolith properties at that site. Next. And then last, the outlier of the group is Compton-Belkovich. So in the UV, it is the darkest region. And like I said, I focus on where the thorium anomaly was measured in that pink box, and it is darker than this Mare-like region nearby. Because it's composed of so many features, it could be that this change that we see, this darker magnitude overall, is because of how much volcanic activity there was, but it is also worth mentioning that because it is a far side spot, it likely has more space weathering. And next. So unfortunately, if I wanted to compare this like the other sites, the WAC footprint did not cover this. So if I wanted to do the normalized to 30 degrees phase angle, so we just have the UV for this one. But even in the UV alone, Compton-Belkovich is a clear outlier. It's possible that this represents the differences that we see is more weathering at Compton-Belkovich, less weathering at the other sites, and that's why we see this difference. But we are comparing to additional data sets. The next. So then plotting everything together, Compton-Belkovich is in black, and we can see a clear difference. Either something's going on different in terms of space weathering, composition, or another regolith property, but it is clearly standing out from the rest of the group. And then we see among the Gruithuisen site, there is differences between the gamma and delta dome. So we see that the delta dome is possibly like Hansen alpha, so that could be in terms of silica composition. But like I said, the gamma dome has these two large impact craters that may be affecting this signal from the region that I averaged. Next. So then, as we see, Compton-Belkovich is missing, but we see the spectral reversal is clear for the Gruithuisen domes. So they do this bit of a switch from the UV through the vis. So we have LAMP on the left and then WAC on the right. There's not really a reversal for Hansen alpha. So when we normalize it to this background highland region, it is relatively flat. So what this might mean is that perhaps the spectral reversal has ties to silica composition, and if we were to see Compton-Belkovich, it would likely have a large reversal as well. Next. So going back, revisiting my science question, how and why does the magnitude of the UV-Vis spectral reversal vary among lunar red spots? So far, we were able to answer the how, but we are not completely sure of the why. So it is possible that there are ties to composition, so these regions are all believed to be highly silicic, but is it because more silicic has less reversal or more silicic greater reversal? We will compare to additional sites to see this. Compton-Belkovich did stand out as an outlier, which agrees with previous studies that I mentioned. So this is likely a combination of the formation of the site as well as the composition differences due to space weathering. So future work, where is this going? The additional data sets we will compare this to, so data sets like diviner H parameter, which directly relates to silica and regolith, will be greatly beneficial. Also lab spectra, however, it is extremely limited to the far UV. Next. And I was just going to say, I would like to thank my advisor, Addie Dove, and then collaborations with Dr. Akbar Wizin and Ben Byron. Thank you.